The purpose of this project is to design a program that simulates the mathematical model of an X-ray machine. We implemented the project using the software MATLAB. During the semester, we studied medical imaging modalities, their evaluations, and simulations analytically. For X-ray imaging system, two different human body parts are used as our dataset, which are the 3D chest CT and 3D CT torso from side. Moreover, two different sources are used, so there are four cases for observation of the process. Two different sources offer us a better understanding of the difference between ideal and real X-ray sources.
Here you can see our 3D CT scan model. For dataset, we used Vowel X Beta library as the source. We prefer 3D CT images since CT is 360-degree projection of X-ray. After creating the 3D model, the bone, muscle, soft tissue, and air are segmented for the purpose of distinguishing them from each other in the downloaded PNG formats. While segmenting the body parts, thresholding operation is used for each pixel by using the RGB of the image. After evaluating each slice and investigating the values of the pixels, threshold boundaries are determined. To give an example, in the figure on the left, there is the original CT image shown. The value of the bone on the rib is 255 on the white area, and the value of the muscle on right is 157 on gray area, are shown as data points. Therefore, since the RGB for white is 255, we set the pixels that are close to 255 as bones. For gray colored parts, since the RGB code value for gray is in the middle, we set the pixels that are between 80 and 200 as muscles. We set the lighter gray colored parts as soft tissue. The determined values are between 40 and 80. For air, we thresholded the values less than 40. The image intensity on the detector of each pixel is changing according to its linear attenuation coefficient. The values for linear attenuation coefficients for bone, muscle, soft tissue, and air are assigned at 7 kV as 0.4, 0.2, 0.1, and 0, respectively. After assigning the coefficients of each pixel according to the threshold, image intensity is calculated. To evaluate the X-ray image, the intensities are summed up from the first slice to the last slice by fixing the location of the pixels in X and Y directions. Then the average intensity of the slices are calculated for each pixel. This provides the X-ray image. For better understanding, the case when X and Y are fixed as 1, 1, the calculation of X-ray image is shown in the figure.
With the ideal point source as expected, X-ray image is shown in this figure. We see the spine, ribs, heart, and organs below lungs. Since heart is occupying more space in Z direction, in other words, it is occupying more of the slices, the color of heart is closer to bone as well as the other organs. Another reason for seeing heart is it is muscle which is more dense than soft tissue. But ribs are very small when we compare with the organs and muscles. Therefore, we lost visibility for ribs. Spine is occupying relatively more pixels, slices than ribs. Therefore, spine is more visible in the image. With the extended point source, it is observed that we lost resolution which was expected, because multiplying the image with sinc function in Fourier domain corresponds to filtering. If we keep the radius of the filter small, the peak of the sinc function will be high for a smaller area, so we allow only small amount of information to pass through filter. In the extended source case, we are allowing more pixels around to contribute, which causes blurring. So, when the extended source is used, it can be clearly seen blurring effect. We applied the same procedure to this image and below. The results are provided. In this case, we realized X-ray projection is not useful for such cases. Here, since we are projecting from side, the organs and the soft tissue is more dominant in overall image. Therefore, different imaging systems can be applied for this case, but we can still observe the blurring effect of the extended source in this example.